had a happy Thanksgiving and didn't forget too much chemistry. We'll start off with just a tiny bit of review and then do some mathematics and then, kind of continue forward. So everyone should have this handout. I actually remembered to print it this time. And what this is, if you remember, is the solubility curve for various things. Now yours isn't in color, so notice, for instance, that two of the lines are in blue. Those represent the solubility of gases, hydrochloric acid and SO2. And notice that the solubility of gases decreases with temperature. And then the rest of them, our red lines, are representing solids dissolved in liquids. And with the exception of lithium sulfate, we notice that those lines increase with temperature. Although where they start at and how quickly they increase is sort of dependent on each specific compound. And then if we, for instance, just pick one line here, for instance, we'll take a look at the che103 line. If I have a solution that's, say, about like right here, where, say, that represents 90 grams of che103 over 100 grams of H2O, does that represent saturated, unsaturated, or supersaturated? Do you even remember those three words? Okay, so this represents supersaturated. And that means that basic Superman flies above the line, did you say? That's not bad.
That's what I meant.
And so supersaturated is essentially there's more than the maximum amount dissolved. You can always rewatch the lectures too if you really want to kind of get that information a second time. And remember that this is unstable. And then if we're on the line, what does that point represent? Yeah. That means the maximum amount is dissolved. And then if we're below the line, that represents our unsaturated solution, meaning that there can be more solid dissolved in it. So notice that this graph has kind of weird units in that it's grams of solute per 100 grams of water. Well, what if we don't have 100 grams of water? What can we do? For instance, if we ask a question like this, and pull out your charts because you're going to need to look on those. That's why I handed them out. You'll also probably need them on your homework, and they'll probably show up on the test and everywhere else that we put things in. So what do we do if the units that we have are not sort of the units we want? For instance, oops, I unplugged that. Plug it back in. Technical difficulties. Cords are coming undone left and right. There we go. So for example, how many grams of che103 will dissolve in 250 milliliters of water at, say, 30 degrees Celsius? So what we're going to need to do is we're going to need to use that chart, and we're also going to have to adjust that chart so that it shows how much it would be in 250 grams. So the first thing we need to do is just look at the chart. So what we want to do is look at that 30-degree line and see what the solubility would be. Now here's where everyone's answers can differ just a tiny amount. For instance, what do you think that line, or where do you think the che103 line crosses at 30 degrees Celsius? What value is that?
46 or 47.
Yeah, 46 or 47. So as long as you pick one of those values, you're going to get the answer right. Now if you pick 36, it's not right. If you pick 42, it's probably not right, because it's certainly over halfway, right? So the first thing we're doing is we're kind of making an estimate. And so, for instance, we would say that there's 46 grams of che103 over 100 grams of H2O. And so this is what we're getting from our chart. And then what we want to do is we have to set up a ratio and say, well, I really want to know what it is for 250 grams of H2O. And so this is sort of my new volume. And so how do we solve ratios? Yeah, just cross multiply. And so you get 46 times 250 equals x times 100. And we solve for x and we get 115 grams of KNO3. So even though the chart is per 100 grams of water, we can use a ratio to determine, you know, it would be what it would be for any volume of water. You guys pretty good with ratios?
Is it math?
Yes. Unfortunately, that means no. So that's one type of problem that we can ask based on this chart and kind of using this information. The second type of problem that we can kind of look at is we can figure out how much more something can be dissolved in, or how much something will precipitate out if, for instance, we change in temperature. So using this information, we can kind of ask a second question. Do you want me to go back a second? No? Okay. What is... Oh, that's the information. Never mind. If the above solution is cooled, to 10 degrees Celsius, how much KNO3 will precipitate out? Now there's two ways we can solve this problem, and it's kind of up to you guys how you want to think about it. So we know that there's 46 grams of KNO3 per 100 grams at 30 degrees Celsius. And we know at 10 degrees Celsius we can estimate it to be about 20. So there's 20 grams of KNO3 per 100 grams of H2O at 10 degrees Celsius. So how much will precipitate out? Yeah, does everyone see where the 26 is coming from? But that's 26 grams of KNO3, right? Per 100 grams of H2O will precipitate out. But remember, how much did we start with in that solution? We started with, remember we have 250 milliliters of water, right? So what we're saying is that we've got 26 grams of KNO3 that'll precipitate out over 100 grams of H2O. But that's, remember that we have 250 grams of H2O, and so then we have X. And so again, you have to have, or solve for a ratio, and you'll get 65 grams of KNO3 will precipitate. That's probably the easiest way, is to kind of take this first part and figure out how much will precipitate out, and then take the second part, so this is the amount that precipitates. The second part is we adjust for the different volume. The other way we can do it is we can say that if I have 115 grams of KNO3 per 250 grams of H2O. Do we have a question?
How did you get the first two, the 40?
This I just looked up on the chart.
Oh, okay.
So that's just reading the values from the chart. Jess?
How did you get the 26 and why are you going over
So 46 minus 20 gives me my 26. So if you take a look on the chart, what we're really doing is we're taking a look and we come over here at 30 and we said I've got approximately 46, right? And then we come over at 10, and we say that that really is about 20, although that's as close to 20 as you're going to get. And so the idea is that if I change the temperature, that's the amount that precipitates. Does that make sense? And then notice that, remember, this chart's always per 100 grams of H2O, but our questions were initially for 250 milliliters of water. And so that's why we're doing that second step to adjust it, because we really have that 250 grams of water. So we're saying, if I have 100 grams, how much will precipitate out? And then since I have 2.5 times that amount, really I'm simply multiplying by 2.5 in the end.
How did you know to look at the 30 degrees though?
Because it says if the above or previous solution.
Oh.
And so we're taking this previous solution that was at 30 degrees Celsius. So the two problems are linked, right? They're kind of the same or not the same question, but they're linked together. And you know what? I'm not even going to show the second way because that just confuses people usually. So we'll do with one way, which is basically figure out how much will precipitate out based on 100 grams and then adjust it to whatever your different volume is at an end. And so that's a real easy or kind of basic problem using both the chart and kind of that concept of, what's the word I'm looking for? Ratios. Okay, so the next thing we want to take a look at is, and we already looked at in chapter 14 about what affects solubility and why it changes with temperature and various things like that. What we want to look at next is basically what affects the rate at which things dissolve.
We only did temperature. We didn't get to pressure.
We skipped pressure, then let's go back and cover pressure. So solubility and pressure. I forgot where we left off, to be honest. I thought we had covered both of those. So if we take a look at it for solids dissolved in liquids, there's basically no effect, because solids and liquids are independent of pressure. If we kind of think about it, the system we're kind of envisioning, we have our liquid and we have our solid, and remember, we're kind of looking at the equilibrium for the solid going into the liquid and then precipitating back out as a solid. Well, pressure is pushing down on the liquid, but we know from chapter 1 that liquids and solids are basically independent of pressure, meaning pressure has no effect on them. Now, you can argue that extreme amounts of pressure will have an effect, but we're talking, what we'd think to encounter on a typical day on Earth, not, at the core of a planet or, in a star or something weird like that. Now, it's another matter for gases dissolved in liquids. Because here, if you think about it, the equilibrium is between the liquid and those particles in the gas phase. And here, if I've got atmospheric pressure pushing down, then I really should expect that equilibrium to change. And so for gases dissolved in liquids, what we find is that increasing pressure increases the solubility. And the way I like to think about it is it literally just pushes the gas into the liquid. That's why, for instance, pop, etc., are bottled under pressure. That's why when you open them, they fizz as the excess is released. Okay, so yeah, I did forget that. So the next thing we want to look at is how fast things dissolve. I think next year we'll have a 1-week crash course in how to write super fast.
You should have one on how to talk super slow.
I think I know how to talk super slow. I just don't want to drink that much. Good to go?
Good to go.
Okay, so the rate at which dissolving occurs. So there's 4 things that affect it, and I'd argue that at least 2 or 3 of them are common sense. Can anyone give me an idea of how I could make something dissolve faster in a liquid?
Heat it up.
Yeah, so temperature. So if I increase the temperature, I increase the rate at which things dissolve. And the reason for that is kind of twofold. Mostly it's because there's increased kinetic energy. Leads to an increase in the rate of the molecules moving and dissolving. If we think about how things dissolve, if I have a big old lump of solid here, and I've got a bunch of liquid molecules, so these are water molecules, and the idea is that in order for a solid to dissolve, the H2O must interact with the solid. So anything that increases the frequency of those interactions, or it increases the intensity of those, is going to lead to an increase in the rate. So if the water molecules have more energy, they're hitting that solid harder, there's more likely to pop off one of the solid atoms and, form a cation or an anion that's dissolved in solution. Okay, what's another way I can make things dissolve faster? Think about it this way. What's a way I can make things cook faster? You guys aren't chefs, apparently.
Well, I'm sure once you say it, I'll get it, but I can't remember.
I think I'm going to make Very good. Smaller things cook faster, right? So if I chop something up into lots of little bits, it's going to cook faster. Same thing if I dissolve something. If I increase the number of particles, or the other way to say that is if I increase the surface area of those particles, they dissolve faster. What dissolves faster, a sugar cube or a spoonful of sugar in your coffee? Yeah. So we can increase, particle size, we'll say it this way, particle size / surface area. So as I increase the particle size, that means I'm decreasing the surface area, and so I decrease the rate of dissolving. Which that means is that big particles have a small surface area, therefore dissolve slowly. If I take a big cube like this,
Why do we have small surface area?
Well, remember, we have to compare the same size of things. So that's what this example is going to show you, okay? So if I have that versus that, the amount of solid is the same, right? At least as same as Jay's crappy drawing skills can make it. But if I take a look at the surface area, it's different. So for instance, if I simply say that this side is 1 by 1, then the surface area, and please realize that normally we'd be talking about 3 dimensions, so we're just going to say that this is a 2-dimensional example. I've got 4 sides, right? So my surface area is 4. But if I count it here, well, each of these is a half, right? And so now I've increased my surface area because each of these cubes has a surface area of 2. So 2, 4, 6, 8. Here my surface area is 8. And so if my surface area doubles, then I have twice as many places that water can interact, so things will dissolve twice as fast. And so this dissolves, and it really is not twice as fast. It's probably some other ratio, but the idea is it dissolves twice as fast because it has twice as much surface area. So when we say that we're increasing the particle size, we're not increasing the amount of matter present. We're just saying that it's in one big lump instead of lots of little ones. So remember that the water has to interact with those sides. And so the more sides or the more surface area that's available, the faster that things will dissolve. Or the opposite of that is if I increase the particle size, I decrease the surface area and the rate decreases.
You said the more surface area available, what?
Well, here, we can phrase this in 2 ways, meaning if I decrease the particle size, that means I increase the surface area, and that means I increase the rate, meaning they're both the same statement, they're just opposites. It's opposite ways of stating it. So increasing surface area increases the rate at which things dissolve.
Because more surface area is available for the H2O to interact with?
Yep.
And the more interaction increases, right?
Yeah, the more that it can interact, the more that will dissolve. Meaning for dissolving to occur, remember the water molecule has to interact with whatever we're talking about. For example, and this is a bit of review, remember what we said is that if I have a solid lump, say, of sodium chloride, the reason sodium chloride dissolves is because I've got a sodium ion that's surrounded by a bunch of water molecules, right? Like this. And then I've got chlorine ions that are surrounded by a bunch of water molecules where the hydrogens are pointed to those. And so this is a little bit of review, but that's due to the opposite attracts. And so the idea is that the larger the surface area, the more water molecules that can interact. Meaning there's more, in order for that to occur, a water molecule has to come close to the solid and pop off one of those sodiums or chlorines that's stuck in the solid phase and surround it. And so the larger the surface area, the easier it is to surround those molecules. What's another way that we can increase the rate at which things dissolve? So if I put a little sugar in coffee versus a lot of sugar in coffee, which amount's going to dissolve faster? You want me to go back? We definitely have to work on. All students from now on must come to class highly caffeinated, fully rested, not worn out from lifting weights apparently. Are 4th graders highly caffeinated.
They don't
They
need
are
to.
now.
But they're highly
And
active.
they get plenty of sleep.
I don't know. I always thought maybe I should become a drug dealer, and if we give everyone a little bit of speed, then
Yeah, that's what you should do then.
us could go twice as fast. Okay, so the third one is it depends on concentration. The higher the concentration, the slower things dissolve. Or another way of phrasing that is the closer to saturated, the slower things dissolve. For instance, if I kind of draw a graph where this is the amount dissolved and this is the time, and if I kind of draw a line up here where this is the maximum, or that's where it's saturated, then for very little amounts it'll dissolve quickly, but as we approach that saturation point, that line levels off. And the reason for that is, if we take a look at it, it's called localized concentration gradients. And so what we're saying is that if I have a lump of solid in my liquid, then as it's dissolving, there's kind of layers in there where there's, it's concentrated, and way up here it's kind of dilute. Meaning that right near the solid there's a lot of dissolved sodium chloride, for instance, if we're talking about sodium chloride, but far away from the solid there's very little dissolved. Have you ever, for instance, just taken a glass of, say, water, if you dump some sugar in it, you can actually see where the sugar solution is at the bottom and it's more concentrated. You can do the same thing with salt and show where you can see the layers where there's different amounts of salt dissolved in the water. Now, obviously, over time, it fully dilutes and this concentration is the same everywhere in the solution. But initially, at least, it's more concentrated right around the solid than it is around the liquid. And so it kind of dissolves faster. The other way to think about it is that near the solid, there's less H2O to dissolve particles.
Is that why you gotta mix them?
Yes. That's why mixing stuff also makes things dissolve faster, right? Like, for instance, if I just dump my sugar into my coffee versus if I dump some sugar in and then stir it up, which one dissolves faster? Yeah. So number 4, thanks to J. Bradley Jr., is already mentioned. So number 4 is basically agitation or stirring. You want me to go back, right? I am not going fast. You guys are just having a Monday and going terribly slow. So near the solid, there's less water available to dissolve the particles. I think we'll skip that part. We'll
Why
skip.
do they say that salt, well, I know it's a myth, but I've been told in my life that salt will make water boil faster.
Boiling occurs, or in order for boiling to occur, there usually has to be some imperfection for the gas bubble to grow on. Adding salt adds some imperfections in there. Whether it's really going to change the boiling point that much,
It's not a myth,
no.
it's busted, but I just was
It's,
wondering
let's put
why
it this way,
people ever thought
it actually will. The effect is so tiny that you'll never notice it for the amount of salt that you would normally add to something. We can, or we will when we start talking about something called colligative properties, which I don't think we'll get to until Wednesday. That describes that phenomenon. But it's such a small change that, like I said, you won't notice it. Yeah, I think I always find it funny because people will say that. I'm like, they're boiling. We're cooking dinner and they're like adding salt to the water. I'm like, why are you adding salt? Because it makes it boil faster.
Well, the Italians on the East Coast, they all do it when they make pasta. They all put salt.
As far as like, do they put a lot of salt or just a little?
No, it's a little, and it's because they told me when I was young.
That's what I mean.
What
It
you
just
do, make
helps
it
the
boil fast.
pasta not to stick together. Doesn't have
No, I'm aware. This is physically what they told me, that it boils faster if you add salt.
Okay,
That's
so
right.
the last one is agitation or stirring. It's kind of a combination of all of the previous, meaning it increases the kinetic energy, a small amount. It increases or it breaks those concentration gradients. What is what? Agitation or stirring.
No, after combination.
It increases the kinetic energy by a small amount. And it breaks the concentration gradients, basically. And so it increases the number of interactions that occur. Okay, I'm pretty sure I took the next set of problems off the homework. So what I'm going to do is we'll talk about or review just one of them. So if you read the book, for instance, they're going to tell you about a bunch of different measurement types, meaning we can have and talk about mass percent, where they tell you the grams of solution dissolved in 100 milliliters of water. We have things called parts per million. We have mass volume percents and things like that. But the one we tend to use in class exclusively is one we've already had. And normally this is not introduced until this chapter, but I hope that since we introduced it already before, you guys can remember this. What is molarity? This is going back to where we talked about it, which was chapter 9. So this is good review for both chapter 9 and this chapter and then in chapter 15. It's moles of solute all over molarity per liters of solution. And sorry, I'm thinking ahead to the next part of the lecture where we talk about something called molality. So we have molarity, and on Tuesday or Wednesday, we'll probably talk about molality, which is another set of units. So we generally abbreviate that with a capital M. But remember, never use in a bar problem. So even though we write, for instance, that we have a 5.0 molar solution of HCl, in a bar problem we'd say that we have 5 moles of HCl per liter of solution. So that's sort of how we use that as a conversion factor. And then it's the same type of problems that we had in chapter 9 that we can kind of ask ourselves in this chapter. So for example, how many grams of NaOH are in 250 milliliters of a 1.25 molar solution? And so we have to go back and review things that we learned in chapter 9 about how to do these types of problems, and also just conversions in general. So if we take a look at this, remember that we always kind of have that question part and the answer part. And so I've got 2 sets of numbers in this. And the second part should be easy. We want to know the grams of NaOH in our answer. The question is, where do I start with? Do I start with the 250 milliliters, or do I start with the 1.25 molar?
No,
Yeah, so this is a single number, or a single unit. And remember, we want a single unit, so that's where we start. Also remember that this is a conversion factor and we never start there. And so we really want to start with our 250 milliliters of solution. So 250.0 milliliters of solution. And since our conversion factor molarity is in moles per liter, we have to say that 1 milliliter is 1 times 10 to the minus 3 liters.
Shouldn't you have milliliters on bottom?
Oh, yep, thank you for paying attention. 1 milliliter is 1 times 10 to the minus 3 liters. And then we can use our conversion factor. There's 1.25 moles of NaOH in 1 liter of solution. Plug that into your supercomputers and you should get 12.5 grams of NaOH.
No, you got another step.
Yeah, there's another step.
Oh, wait. Oh, you're right. I'm doing the harder problem. We got to go from moles to grams, silly J. 1 mole of NaOH is 40.0 grams of NaOH. Sorry, I was looking at my notes and I was skipping the problem where we just did moles and we went straight to grams. But that's okay. So this is awesome. We use molarity, we use molecular weight, and we use metric conversions. So this is really good review for the final. That's one of the things I like about the book. It seems like a lot of the topics that we need in chapter 14 and 15 are darn good review for what we're talking about in the final. So if you do all of that, you should get 12.5 grams of NaOH. Does this ring a bell to people? Is this kind of going back in time and thinking, okay. Okay, so next question is how do I make 150 or milliliters? Actually, let's rephrase that. How many grams of NaOH is required to make 150 milliliters of 2.0 molar NaOH? Actually, that's the exact same question. Yeah, never mind. Screw that. That's a waste of time. Okay, let's do our next topic, which is what's the word I'm thinking of? Oh, dilutions. Except I can never remember if it's 1 or 2 L's for dilution. I think it's 1, isn't it? What dilutions are is we take a concentrated solution and we make a dilute solution. And we've actually done this before. You guys might remember that we did this in experiment X, which was that spectroscopy one. You guys remember the formula we used for this? You can also think about this as taking frozen OJ and making orange juice. So M1 V1 equals M2 V2. What this is saying is that the molarity of solution 1 times the volume of solution 1 has to be equal to the molarity of solution 2 times the volume of solution 2. So M1 V1 equals M2 V2. Live it, learn it, never forget it. It's one of those common things that it actually pops up in lots and lots of places. For instance, if you're baking, you can use this to change the size of your recipes. If you're mixing up anything to do with oil and cars and engines and antifreeze and things like that, kind of comes in handy. If you're making orange juice, this is essentially what you're doing. So for example, if I have, and I don't even, my notes are horrible. I just make the problem up at this rate, because if I have 25.0 milliliters of a 2.0 molar solution, how much water, or what is the final volume of a 0.35 molar solution? Meaning I'm taking 25 milliliters, well, so here's solution 1, and then I'm asking something about solution 2, and so the idea is that if I have a 2.0 molar solution, and I've got 25 milliliters of it, and I make a 0.35 molar solution, how many milliliters of that solution do I make? Yeah, so does everyone know how to solve that algebra equation? So x equals, of course Jay forgot his calculator. Who's got a calculator? Brittany, can you plug that in real quick? 2 times 25 is 50. So what's 50 divided by 0.35? We'll call it 143. So what that means is that I can make 143 milliliters of a 0.35 molar solution. Now, here's where we have to be careful. Notice that this is the final volume, right? How much water did I actually add to that solution? Well, I have 143 milliliters is the final volume, but I started off with 25 milliliters, so what's that divided minus 25, Brittany? I guess I can borrow. 13 minus 5 is, oh gosh, it's a bad day. Is that 7? 8? Just kidding. 118 milliliters of H2O added. So be careful with the phrasing of these questions. For instance, I can also ask how many milliliters of H2O do I add to make a 0.25 to make, say, 100. Wait, how many milliliters of H2O do I add to make a 0.50 molar solution of HCl from 25.0 milliliters of a 5.0 molar solution. So notice this, the work is still the same, meaning here's solution 1, here's some information about solution 2, and so I'm still taking 25.0 milliliters times 5.0 molar, and that's still equal to 0.50 molar times x. When I solve for x, in this case, since I just made it different by a factor of 10, this must be 250. Brittany can check my math, since she's this only, well, I shouldn't say she's the only student that brought a calculator. I see several others out. But since I didn't bring my calculator, is that really 250? See, I made the numbers up better this time so that I can do the math in my head.
Yeah.
So, but remember, since the question says how many milliliters of water do I add, I don't want the 250, I want the 250 minus 25, which is 225 milliliters of H2O. So notice that sometimes we ask how much water we add, and sometimes in the previous question we ask for the final volume. And so kind of be careful with the phrasings of these dilution type questions. Oops, sorry. Oh, there's where all my good examples are. Wonderful. Oh well. We'll have to remember that it's out of order next year. So let's take a look at what we got for the rest of the week. Tuesday, Wednesday, Thursday, Friday. And we're going to say that this lab is due on Thursday, meaning I want you to have completed the lab by Thursday. Whether that means you come into class on Thursday, you finish the 2 little parts you need and turn it in, that's great. If that means that, you have to work on the write-up on Tuesday and Wednesday and maybe come in some other time to schedule it, we'll do that. Let's say that, and we're going to kind of speed things up. Homework 14A and B are due on Tuesday. Actually, wait, we still have all of chapter 13 that most of you hadn't due. So let's put it this way. Homework chapter 13, A through, was it C?
Yeah.
Is due. And then we'll say on Wednesday, homework chapter 14, A and B are due. And so on Wednesday, we'll finish chapter 14. And we'll start chapter 15. And then I'm guessing we're going to have a test on chapters 13 and 14, mostly so that we don't have 2 tests the last week of class. And then what we'll look at, well, next week is the last full week, and then it's finals. So what we're going to look at is we'll do chapter 15, and 16. We'll have a test on actually, we'll probably do it this way. Chapter 15, 16, review, test on chapter 15, 16, and then we'll have a review for the final on that day. And so then homework 14C is due on Thursday. So we're crushing things together a little, but what we'll do is Monday from 6 to 8 I'll be here, and Wednesday probably from 6 to 8, although I'm not going to guarantee that one yet, so probably. Meaning I'll be here plenty for people to ask questions, and we just have to buckle down, and if you didn't finish chapter 13 homework before Thanksgiving, well, you dug yourself a hole. That's life. We should have had class that Friday, too.
You are so nice, Jay. Thanks so much for that. I'm trying to display.
So my office hours will be in Striegel today, and they'll be in